Class 14, we're dealing with flexible mechanical elements. Just a brief little discussion on the V-belts. We already covered flat belts in a previous section here. Some of the differences, and I think I actually talked about this in some of the beginning right here, between V-belts and the flat belts. The V-belt has a narrower, let's say, sheave here, angle, than the belt itself. So it creates sort of a kind of, you can see, I like this picture right here from Collins. It gets a little smushed in there, and when it has under tension, it causes that little deformation there, but that really increases the amount of friction that's going to take place. You can see this from this other book right here, Juneval. Shows the like, maybe it's not really a free body diagram because they're actually showing the sheave right there. They shouldn't for the free body diagram, but it shows the normal forces that are taking place as part of this right here. I mentioned there's two different kinds of V belts based on their construction. And you can have V belts. You can put multiple ones in line. I guess you could do that with just about anything, but it's with the flat belts. But I think it's a lot easier to do with the V belts because you definitely have an orientation. One of the things they can't do is they can't like switch between pulleys or sheaves like you can with a flat belt. Timing belts are really important in engines to coordinate the valve opening and closing, the intake and exhaust valves, and also in diesel engines they also control the they're moving on cams, but they can also be integral in controlling the fuel injectors. Now that's actually kind of like older engines. Now modern engines will actually have electronic timing. Because by doing that, they're able to like shift and change when the valves open and close and when the fuel injection might take place. So for an example, in diesel engines, they have a fuel injector as opposed to having a carbureted intake. That is that the air comes in clean in diesel, and then fuel is injected directly into the cylinder at a particular timing that decides when ignition takes place, as opposed to a gasoline engine, which generally has either a carburetor or it can have fuel injection, mixing air and gasoline together outside of the cylinder, and then it comes into the cylinder and it does this explosion. But that timing in older engines was done with a belt. Right, or it could be done with gearing too, but it's most often there'll be some type of timing belt or a timing chain, which will connect the output shaft, like the crankshaft, to a, as you can see right here, in the timing belt has a whole number of things that it could also move onto this, but it will move the camshaft, which will then open and close the valves. So like at every exact location of a crankshaft, it would decide that a intake or exhaust valve would be opening and closing because of that. But with modern engines and trying to reduce fuel emissions, subtly changing that timing depending on the speed of the engine, right? Because it takes time for fuel and air or exhaust, burnt up exhaust, to escape out of the exhaust valves, or the clean air to come in, right? So you might want to change when you open and close that depending on how fast the engine's going, because that mass has to come in and it has to go out. So if you just have one timing that's kind of set for every speed right there, you can have the exhaust valve been opening too early and can let unburnt fuel out right there, or anyway, you can change the emissions. You can also change the temperature. That's some of the nitrogen oxides are dependent on the temperature, and so you could actually kind of change the amount of fuel as well that gets injected in diesel engines. So some of that is built into the tier standards. But anyway, you should know that there's timing belts, right, in older engines, and that it has kind of changed a bit. But you can see that they have these little like teeth, very much like gears on there, and kind of similar to chains in some respect. There's a little bit more flexibility in these rubber timing belts than there is in chains. But one thing you want to make sure is that you get this changed in your vehicle, right? You don't want to go around past 100,000 miles without getting your timing belt changed. I guess it depends on what engine you have, but most of the time I think it's right around 100,000 miles. You want to get that timing belt changed, because if this were to go, the valves could be down while the piston comes up. And it's not true in every car, but in many cars, the valves actually go down further than the top dead center. So you could have catastrophic damage. It wasn't just like the engine won't just stop. It will go be kaplooey, and pretty much the crankshaft will get bent and it'll be ruined. So get your timing belt changed. It's something you could probably do yourself. I understand it's not, and on some engines isn't that massively difficult to do. And we can also use chains. I guess it would be timing chains. I think on some European cars there are kind of more timing chains. I don't know that for a fact, but I seem to recall. All right, so chains, if you have a bicycle, hopefully your parents got you a bicycle, right, as a kid, maybe a tricycle, but anyway, hopefully a tricycles, I guess, don't have chains, right? The big ones that like weird adults like to drive, the recumbent ones, like, oh, what the hell's up with those people? But you have roller chains, and they all have these kinds of features where we have like little bushing and pins and a roller, and you have these little plates right here, and usually there's going to be some kind of like connecting link at some point right here that you can take off so that you can change the length of the chain, or sometimes even just to be able to put it on, you need to have some type of link somewhere along the lines where you can disassemble the thing. So look for that sometime on here. Right? It's a good idea to look for it. But anyway, you get on your chainsaw. You can have you could find a chain similar to this that they have extra little things that are attached to the plates that can chew up the wood. But there's different types of these different chain links. Some of the geometry that's kind of interesting and important as part of chains to notice. They have this thing we call like the chordal length, right? So I'll try to sketch it on there if I can find my little pen. Of course, these pens, so this pen works terribly. But you could see that we could think of this thing as being like segmented right there, right? That the length of these links right there, and in these different positions, like when it's up, it's not going to have the same velocity here as it is going to have velocity here, right? I guess this is actually showing the line of approach, so I drew the arrows the wrong direction. But you get the idea. And the result of this, of the fact that it doesn't have, that the geometry is kind of changing right there, it has a bit of a speed variation right there, so the fluctuation. Now you can reduce that by having lots and lots of sprockets right here. But you could see the typical sprocket is for the small side of is 17, right? So that's about as that's about the minimum that they recommend is 17, although you can get smaller, and it is like often done according to the textbook. But you can see that you have like something over than a 1% variation in speed. So that means it's not conjugate action. That's interesting right there. Note that you could put chains, you could have multiple ones. And I think when you have a timing chain, I think they're often done that way. I've seen that right there, especially on like high performance vehicles. I seem to recall seeing that. Okay, so other things that we want to know about chains. All right, so they have something called the angle of articulation, which is kind of an easy, interesting thing. It's like if you were to, let's see if I'm going to say this the right way. If you're going to take a look at the next guy down here, that angle drawn through there, that would be the 1/2 of the angle of articulation. That's what they call it in some books right there. Which is actually going to be like that right there. This is the full angle of articulation, they would say. Wear and surface fatigue of the rollers kind of determines the life in chains right there. So it's actually these rollers right here, and the surface wear that's happening on them is often the thing. So you require some good lubrication taking place. So there's multiple different kinds of lubrication that can be done on chains. It's good. We're going to take a look at, for the example, take a look at the Martin Sprocket catalog, and you can see some of the things that it's maybe organized, easier to digest than some of the ones in Shigley. So like when you look up in a catalog for chains, usually they're going to be rated at about 15,000 hours at full load, right? So when they give a power capacity, that's what they're using at. 15,000 hours for full load, 100 pitches long, right? So each pitch is one chain link, really, in length right there. So, and it'll be rated for 2 17-tooth sprockets, right? So just like bearings, what they'll do is they'll have a machine that's with a 17-tooth and a 17-tooth, and the chain is 100 links long, and they'll run it for 15,000 hours, or they'll figure out how much load capacity it can withstand for 15,000 hours. So they might test it for a certain amount of time at a certain load and see, or fail, if it put it at a certain amount of load and see when it like fails or what they consider to be failure, and then they'll use a conversion to back out through that. So some of the equations that are associated with chains, I wrote down a bunch of them. So let me see. I will let me open up my thing here, and I will open up my camera. It didn't give me the last ones. Okay, I'll go camera. There you go. Open up the camera here. Let's see if it's going to give me the right one. It sure did. Right here. Okay. If I can just figure out how to get that over there. All right. So some equations that are kind of important to us, or I felt that they were important. I think the one that I found to be most intriguing from a standpoint that we had similar to the life expectancy of a bearing, right? Remember that bearings had something like this right here, constant. We were able in chains to find something similar. Let me open up let me pause for a second. Okay, so here's what I thought was one of the more interesting equations to take a look at. All right, so once again, the power rating, and they're calling that H2 right there, is going to be dependent on, can be done with a relationship where you can adjust it for when you have something an off or a different setup, right? So for instance, the number of teeth in a sprocket, right? It's the horsepower rating that you're going to see in the catalog is going to be dependent on 17-tooth sprockets, and so we have that right there. Or we have 100 pitch lengths right here. So we have something different, or if you have different hours, and you could say that it's sort of like quite analogous to what we have for the for bearing life right there. So that's sort of an interesting thing if we want to try to change it. They're pointing out that like you have this type of relationship is the similar type of treatment to bearing life. So I found that was kind of interesting. So like we'll go through the example in the next video right here. You'll see that this is like an excerpt right here. This is a catalog excerpt from. Did they tell you who it's from? No, I guess it's just from an ANSI standard, but you can see it's a two-part catalog. One of the things you can see that have different type A, type B, type C, and then type C prime. These are all different types of lubrication methods, right? So you might have a manual or drip lubrication to type A. So like in your bicycle chain, you just take a little oil can, squirt it, or you might have a bath, some type of thing that's splashing oil up into it, and like it might actually dip into some oil and spread it around, or it might be inside a housing where oil gets sloshed around with maybe a disc on a shaft that throws oil around and gets it, make sure that it gets oiled up. Or it could need an oil stream, right? So there might actually need to be on an lube oil system at least a little bit of a takeoff right there, so they'll have like maybe a little nozzle that's like putting oil onto the chain all the time. Right, so they could have different setups depending on the machine and the complexity of the thing and the importance. But you could see that, like for different types of chains, you could see that these dashed lines right here will tell you what zone you are in for that type of lubrication, and that could make that might mean that you'd want to make a decision on whether you want to go to that size. And so the strategy, though, is maybe you want to use multiple chains, multiple side-by-side chains to reduce this power. But by the way, it isn't completely a linear thing right here. So if you have multiple chains, what you do, or multiple strands, you use this factor K2 instead. So like if you have two chains, it isn't. And by the way, two chains, by the way, then you would use like 1.7. You think you might, do we have two chains, use 2? No, you use like 1.7. For 3, use 2.5. And we'll actually, if you take a look at Martin Sprocket, let's see, do I have Martin Sprocket open? No, I do not. So let me pause 1 second here. All right, so under useful links and resources, I think he's actually under gears right now. I haven't made a chains section right here, so but I did put in my Martin Sprocket here, and I think I went Martin Sprocket engineering right here, and you can check out well, they have the sprockets, of course, but here's the engineering start. They start to give you dimensions, sprocket nomenclature. Here's some chain dimensions, sprocket dimensions, hub dimensions, and then they start to go into some selection procedure right here, right? So they talk about different drive positions. These are all good information. They give you a step-by-step thing. It is not necessarily as much calculation as much trying to decide which chains to use or things you need to make sure you can consider. And then they have a pretty straightforward and simple example right here. Now, here's some more engineering equations to use, and you'll be familiar. Some of these should be familiar to you. These even have like a little thing like you would fill out like in your step-by-step procedure, and maybe you would do that before talking with the sales engineer to decide on what to pick. And they do have chain drive engineering, various things to assist you, and equations. These are similar to what you will see in the book. In some respects, there's a few differences. One thing that might be, these are all just diameters of things. When we get down to page, here you go. This one's very difficult to read from this excerpt, so I found a better one. But this is sort of like a quick selection guide type of thing. So I had one that was like improved resolution right there, right, so that you can see this a lot better. Yeah, so you can actually see this part of the thing. but you would pick the RPM of the sprocket, right? And then you would come along here and you would see the number of teeth, although you could see that they're different right here, right? So these are the different categories of chain numbers, right? So if we were to take a look back at Shigley to make a comparison, you would see here's the chain number, the A and Z chain number that's as part of this thing, and here's the rated power, whereas for this one right here, the rated power is this number of strands right here. So you would go like to, if you want to go to one strand, and you could pick out what the power is going to be for 17 teeth. So let's see what that would be like. Let's see if it works right here. For an 80 and 17 teeth right here, we're saying that we have a 10 horsepower. Of course, that's going to be intersected with 200 RPM. So let me see, 200 RPM, an 80 and 17 teeth. It should be 10 horsepower. Let's see if that works out. So here's an 80, and here it is right there. So there you go. We were able to see. So you see that these two are comparable to each other. You could also see that they do have catalog pages as well. Here's one where they're giving you sort of a another like range of these. Actually, I'm not quite sure what they're saying. This sloping lines represent horsepower ratings for 17 tooth sprockets. So this is a quick selection guide, I guess, to try to give you an idea of what range you're to go into. Although I'm not sure what these lines represent, so I should look at this a little bit more closely. But you can see right here we have a pitch of 25 and a pitch of 35. These are like the chain numbers right there, right? So that okay, that's the pitch length, and here is the chain number 50, right? So we just looked at 80 a minute ago, right? And we had 200 right here and 17 teeth right there. So there you go. Here is another type of chart to look at, right? So you can see that we have like 3 different ways that we've seen already to try to pick out what the power rating is going to be. So that's kind of long enough of a video, and I'm going to do the example in the next one. And when I do that, I will go through and look at some of the more important equations.